welcome. Today we'll be doing the 2012 AMC 8. Just to test things out, just make sure to DM chat relay, which should be a bot in the room right now, and then your messages will pop up here. I'm already seeing some messages, which is great. Hello, hello. Before we begin, just make sure to change your Zoom name to a fake name because this meeting is recorded, so it's just to protect privacy. And then make sure to head to this link over here, and that will bring you to the 2012 AMC 8 problems that we'll be going over, just so that you can follow along as we go over them. So, yeah, just make sure to send something to chat relay just to make sure everything's working, because this is kind of how we interact with each other, because that's the only way we actually can see your ideas is if you send something through chat. Okay, so I'll just introduce our co-TA for today. So my co-TA is Kevin, and he was a USA JMO winner, which is super impressive because first you have to do good on the AMC 10, which is harder than the AMC 8 because 10 is a larger number than 8, supposedly. And you also have to do well on the AMI. And then after that, you also have to do really well on the USA JMO. So it's super impressive. And he also is a two-time AMC 10 Distinguished Honor Roll winner, which means that he scored super high on the AMC 10. So he's super good at math. And outside of that, he likes teaching math and also meeting new people.
Yeah, nice to meet everyone. And here, my co-TA is Shelly, who is also really good at math. She represented Nevada at Math Counts Nationals and was the state champion at Math League, which is, really hard. So that's super impressive. In addition, she is the, I don't know how to pronounce that, secretary of her school's math club. So like she does like two things at once. She does treasurer and secretary. So, very talented. And outside of math, she also enjoys biology, physics, video production, piano, and teaching. So, yeah, that's really cool. And um, I guess we can get started today with the first problem. So, again, if you don't see where the problems are, you can visit the link, I believe that should be sent in chat relay. So basically the first problem, I'll just go ahead and jump into it. Rochelle uses 3 pounds of meat to make 8 hamburgers for her family. How many pounds of meat does she use to make 24 hamburgers for a neighborhood picnic? Now, when I look at this problem, the first thing I'm thinking about is rates because or not necessarily rates, but like ratios. Because we have, a certain amount of meat that we can use to make a certain amount of hamburgers, and we kind of want to convert that into more, or we want to convert that for a different number, right? So when I'm doing this problem, I want to set up a ratio equation somehow. So we know that she uses 3 pounds of meat to make 8 hamburgers for her family. So 3 pounds, so 3 pounds equals 8 hamburgers. And what this means is that, every hamburger is going to use 3 divided by 8 pounds of meat, because if we have 3 pounds of meat that can make 8 hamburgers, well, we just divide by 8 to get 3/8 pound of meat is 1 hamburger. Now to make 24 hamburgers, we just want to multiply this by 24. So both sides of the equation, we multiply by 24. And, 3 times 24 divided by 8 equals 9. So with 24 hamburgers, we're going to use 9 pounds of meat. And that's how you do the first question.
Okay. Awesome. So it makes sense that we get a number that's larger, although I guess none of the answer choices have an amount of meat that's less than the original, which is good because if you're making more burgers, you probably should be using more meat. Otherwise, it doesn't make sense. All right, so let's head over to number 2. So number 2 says that in the country of East Westmore, statisticians estimate that there is a baby born every 8 hours and a death every day. To the nearest 100, how many people are added to the population of East Westmore each year? Okay, so immediately I'm seeing death every day and then baby that's born every 8 hours. And there's 24 hours in a day. So I'm thinking that we could do something that's like how many people are added to the city every day. So just to put something over a common unit makes things easier to work with. So if there is a baby born every 8 hours, yep, as math is saying, there should be 3 babies a day just from this. So we're not including the deaths every day yet. So this should correspond to 3 babies. And then I'm seeing lots of you guys are saying that this is actually corresponding to 2 people every day because we also have to account for the singular death per day. So actually, let's put per day. So we have to subtract 1 from this count because someone dies every day. So therefore, our actual rate is 2 every day. And now we have to convert to every year. So in a year, there's 365 or 366 days. This actually isn't really a concern whether it's a leap year or not because it's asking for to the nearest 100. So 1 day probably doesn't matter too much because we're only having an accounting for a difference of 2. So we can just assume that it's 365 days. And all we have to do is 2 times 365, which is about 700. So therefore, the nearest amount is B, 700.
Yep, that's exactly right. And now we can move on to question number 3. And I just want to point out both of the first 2 questions, they kind of have to do like a bit of rates, right? Because to do them, we have to kind of figure out, one or ratio. So we need to figure out one ratio and then we need to multiply by something to figure out a different ratio. So that's kind of cool. And I guess we can move on to question number 3, which says, on February 13th, the Oshkosh Northwester listed the length of daylight as 10 hours and 24 minutes. So the sunrise was at 6:57 a.m. and the sunset at 8:15 p.m. So the length of daylight and sunrise was correct, but the sunset was wrong. So we want to know when the sun really set. Now this problem is kind of confusing, mainly because the way it's worded, right? Like we aren't really sure what we were trying to figure out. So it tells us that the sunset is wrong. So the sunset isn't actually at 8:15 p.m. So we want to figure out when the sun really set. But we know that the sunrise was at 6:57 a.m. So we know that it starts at 6:57 a.m. and 10 hours and 24 minutes elapsed. And we want to figure out when it ended. So we want to figure out when the sun set. So we essentially kind of want to add 10 hours and 24 minutes to 6 hours and 57 minutes to get our final answer. And so let's just do this. Obviously, like, you can't really add it in this way because we'll end up getting, because 57 minutes plus 24 minutes is going to be over 60 minutes. So that obviously won't work, but we can actually modify that later just to see what happens. So if we add 6 hours 57 minutes to 10 hours 24 minutes, we get 16 hours plus 21, or sorry, not 21, it should be 81 minutes. But we know that 81 minutes is just 1 hour plus 21 minutes. So we end up getting that 16 hours plus 1 hour is 17 hours plus 21 minutes is our final time that's elapsed. And since we know that, so the real time will be 17:21, but obviously we can't have, so there'll be 17 hours that have passed and 21 minutes that have passed, but we can't just say 17:21 and call it a day, right? Because remember, there's no like anything above 12 unless you're using military time. So we want to convert this to PM. So 17 hours and 21 minutes passed since the day began means if we subtract 12 hours, that means it's 5:21 p.m. because we want to subtract 12 hours. So we end up getting that the total time of the day when the sunset comes is 17 minus 12, which is 5, so 5:21 p.m. And that's how we solve question number 3.
Yeah, and I really like the way Kevin did it because he separated it from hours and minutes. So basically what he did was he added the hours to the hours and then the minutes to the minutes. Although the issue with that is that it gives you military time. It was like 1721, which isn't one of the answer choices. And also it doesn't really make sense in the context of this problem. So be sure to convert it back into, I'm not sure what it's called, maybe standard time with the AM and PM stuff. Another way you could think about it is adding like the units separately. So for example, like adding the hours first and then the minutes. So for example, if you're adding like the 10 hours first, you can just count ahead by 10 hours, taking for account when you change from AM to PM. So something like 7 to 6, sorry, 6:57 to 7:57, 8:57, 9:57, 10:57, 11:57, 12:57, and then going to 1:57 and so on, and then adding the 24 minutes. Or you can notice that this 6:57 is really close to 7 o'clock. So you can add the 3 minutes first to make it 7 a.m. to make it sort of a nice round number, and then proceed to add these units. Okay, so let's move on to question number 4. So problem number 4 says, Peter's family ordered a 12-slice pizza for dinner. Peter ate one slice and shared another slice equally with his brother Paul. So what fraction of the pizza did Peter eat? Okay, so I'm seeing some people in chat are saying that we could just set our units to be the number of slices so that we avoid weird fractional numbers. So we know that the total number of slices is 12. And then we can count how many slices that Peter eats and put it over 12. So we know that Peter ate one slice, so we have to add 1 at the top. And then he shared another slice equally with his brother Paul. So that means that Peter ate an additional half a slice because he shared it equally with Paul. So you have to add another 1/2. And now you have to be careful because not only do you have a fraction as a whole here, but you also have a fraction in the numerator. So you have to keep those separate. So at the top you have, you have 3/2, which is all over 12. And then this is equal to 3/2 times 12. And then we can cancel the 3 with a 3 at the bottom. And then this gives us 1/2 times 4, which gives us our answer of 1/8, which corresponds with C.
Yep, that's exactly right. And you can see that for this problem, something that I think Sherry did really well was setting up her equations like very cleanly. So basically, we didn't really have to deal with a lot of messy and complicated variables, and that was really great. So whenever you want to approach these problems on your own, always try to set up your equations like really cleanly, so the computation ends up really simple. So now we can move on to question number 5. So question number 5 says that in this diagram, all the angles are right angles and the lengths of the sides are given in centimeters. Note that the diagram is not drawn to scale, so we want to figure out what x is in centimeters. And yeah, I think Sherry has a good diagram pulled up on her screen. So basically for this problem, the main idea is that, essentially this is all the angles are right angles. So if we kind of visualize it, all the lines, so all the line segments or all the sides are going to be either like left or right, or they're going to be going up and down. So for this one, you can kind of see that x is going to be one of the up and down line segments, and we want to figure out what line x's length is. Now, something that's really crucial to this problem is that since, I guess you could think about this as like kind of a closed loop, right? If you imagine like being on one vertex of this diagram and just moving along the entire thing until you go back to where you came from, as it turns out, you're not actually going anywhere in total. So essentially what this means is that, all the increases in height and all the decreases in height are going to be the same, if that makes any sense. And I'll explain this in like more concrete terms, I guess. So what this means is that like the left side, so if you imagine, I guess maybe an easier way to think about this would be if you drew a rectangle around the entire diagram, you get one big rectangle, and the height of the left side is equal to the height of the right side because they have the same height, right? So if we look at the height of the left side of this diagram, well, we can just compute the height of the left side as 1 plus 1 plus 1 plus, so 1 plus 1 plus 1 plus 2 plus x. And so this is the left side. And we can also compute the right side as 6 plus 1 plus 2 plus 1. So equals 6 plus 1 plus 2 plus 1. So which equals 10. Now what this tells us is that we actually can, we can see that 1 plus 1 plus 2 plus x is going to have to equal the height of the left side, which is 5 plus x. So 5 plus x is going to equal 10. So x is going to equal 5. And based on that, we can figure out that the length is going to be 5 centimeters. And that's our answer.
Yeah, awesome. So I really like the way Kevin explained it because he said that all of this vertical part on the left side will have to equal all of the vertical part on the right side. And he explained how if you drew a rectangle around it, if I can draw straight lines, draw one over all the way down and around on this side, and then we do the same thing on the other side. Oh, that's not straight. Okay. We go over, down, and this way. Okay, these lines are not very straight, but pretend they are. This whole entire length down will have to equal this entire length down. And that's just equal to these orange parts. If you kind of draw more straight lines this way, you'll see how the orange parts here, the orange slices, will have to correspond with the pink slices on this side. So then now you just set up this equation involving x here, and you get the same thing of x is equal to 5. So pretty cool problem. And notice how there's a 2 up here. You will never have to use that because this is the horizontal part, and that's not involved with the vertical part. So we don't have to worry about that. Okay, so let's move on to number 6. Let's see. So number 6 says that a rectangular photograph is placed in a frame that forms a border 2 inches wide on all sides of the photograph. The photograph measures 8 inches high and 10 inches wide. What is the area of the border in square inches? Okay, so let's just draw this photograph. So again, this is really testing my ability to draw straight lines. Okay, it looks something like this. And we're given that, okay, well, maybe I should have drawn it longer, so longer on this side. Like this, sort of. So it says that it's 8 inches high and 10 inches wide. So that means this side here is 8, and then this side here is 10. Okay. And then, yeah, I'm seeing exactly what some of you are saying. We can draw this photograph first and then draw the frame around it. So what I mean by that is you have this photograph, and then we're given that the border is 2 inches wide on all sides of the photograph. So for example, if we start on this side over here, then to draw the border, we go out 2 inches this way, and then we draw the border right here. Same thing on the top. On the top, you go up 2 more inches. So then you draw up this way. And then on this side, out this way, and then same thing on the bottom. So eventually, let me switch to a different color. Eventually it'll look something like this, the border. Okay, that is not a straight line. Pretend it is. Yeah, so I'm seeing some of you are saying that the border is bigger than the photo itself. Ooh, okay. Perhaps this is a spoiler to our answer. Let's see if that's really true. So I saw someone said that the border would be 12 by 14. And why that is because this part over here is 2. Let me label that. So this pink line here is 2, and so is over here. This area over here is also going to be 2 because we know that the border is 2 inches wide. So therefore, this length entirely has to be this 10 up here, plus 2 here, and then plus 2 here. So therefore, that entire length is going to be 14. We draw all the way this way. Okay, and now that we have this length, now it's time to find how high it is. So we know we can do the same thing. So we know this part over here is 8. And then since the border up here is 2, that part is 2. And then the border down here is also 2. So then this entire length here will have to be 8 plus 2 plus 2, which gives us 12. And then now it asks us to find the area of the border in square inches. Well, what we can do is we find the whole area of this rectangle, subtract the photograph, and then that should give us the area of the border. Because what we're essentially doing is this entire rectangle and then subtracting the inner rectangle, which is what we don't want. So that will basically just be 12 times 14 minus 10 times 8. And now it's just a couple calculations. So 12 times 14, that should be, let's do it on the side. 12 times 14 gives us 140 plus 28, which is 168. And then 10 times 8 is 80, so we have to subtract 80 from that, which gives us 88. And so that corresponds with answer choice E, which, yes, is indeed a lot, much more than the area of the photograph.
Yeah, and that was a great solution. So I guess just like going over, I think like using computing the areas like that was really smart because you really like, I guess you kind of avoided like the border problem and essentially you just did a larger area minus a small area, which is a really smart way to think about the problem. Moving on to question number 7, we see that Isabella must take 4 100-point tests in her math class. Her goal is to get an average grade of a 95 on the tests. So her first 2 test scores are 97 and 91. And after seeing her score on the 3rd test, she realized that she can still reach her goal. So what is the lowest possible score that she made on the 3rd test? So when I'm looking at this problem, she realizes that she can still reach her goal, right? But her 3rd test is obviously like pretty low. We want the score to be as low as possible, but after the 4th test, she still can reach her goal. So we can just say that the 4th test is going to be 100, right? Because otherwise, let's say if she got 99 on her test, well, it would be like better for us to make it 100 because then we could decrease the 3rd test's score. So it's always optimal to make the 4th test as high as possible so that the 3rd test can be as low as possible and the average still stays pretty high. That's kind of intuition we want to get from this problem. So the average grade of all 4 tests is going to be 95. So the total sum of all the 4 grades is going to be 95 times 4, which is 380. So we know that the total sum of all 4 tests is going to be 380, and we know that 3 of the tests are 100, 95, and 91. 97 and 91. So we want to figure out what the 4th test is. What the score of the 4th test is. So we can see here that some of the 3 tests we already know the scores of is 197 plus 91, which is 288. So 288 plus the 4th test is going to equal, or the 3rd test is going to equal 380. So x is going to be 380 minus 288, which equals 92. So 92 is the lowest score that she could have gotten on her 3rd test and still maintain a 95. That's how you do that problem.
Yes, also, yeah, so I think the main point, like the biggest realization, is that the 4th test has to be 100 because that is how we're going to make this 3rd test as low as possible. Because the lower this score is, the higher that this 3rd test has to be, and we don't want that in this case. So supposing that on her 4th test she gets the highest score possible, makes it so that this third score is lower. And yeah, 92 honestly isn't too bad. It sounds like she's in a really tight situation, but maybe it's that 91 that did it. All right, so let's look at number 8. So number 8 says that a shop advertises everything is half price in today's sale. That is a very big sale. Wow. And in addition, a coupon gives a 20% discount on sale prices. So using the coupon, the price today represents what percentage off the original price. Wow. If that existed in real life, I would buy everything. But unfortunately, probably the retailers wouldn't make much money. Okay, so if everything is half price off, well, that tells me that every price is going to be, like, suppose something is worth P. That's how much something costs. Well, today it's going to cost 0.5 P because it's half off. So then we apply this coupon, which says that it gives a 20% discount. And a 20% discount means that you have to pay 80% of the original price, not P, but this price here. So that means we take 0.5 P times 80%, which we can write as 8 over 10. We could also do 4 over 5. Let's actually do that so it's more simplified. So, and also let's write 0.5 P as 1/2 P. So everything's in fractions. So 1/2 P, then we multiply by 4 over 5 for the coupon. And then this should equal 2 over 5 P. And now we can say it's 40% and we're done. Well, we have to be careful here. Actually, the wording here is really evil because it says the price today represents what percentage off the original price, not of. So this extra F in the word means that it's asking how much that you don't have to pay. So if it was of, then we can run away with this 40% and we're done. But unfortunately, we're not quite done. And they also gave you an answer choice of 40. That's so evil. Okay, well, the price that you don't have to pay, well, that should just be P minus 2 over 5 P, which is 3 over 5 P. And that's going to be 60% of the original price because 3 over 5 is 0.6, converts to 60%, which gives us our final answer of D.
Yep, and that's a really smart solution actually, because essentially, we can, like, even though it's like this wording is pretty tricky and it's like hard to understand, I think you did a really good job on like making it really easy to understand because of the way you set up your equations and explained everything. So that was really cool. So we can move on to question number 9, which says the Fort Worth Zoo. Fun fact, I actually live near Dallas, which is like really close to Fort Worth, and the zoo there is very cool. So it has a number of 2-legged birds and a number of 4-legged mammals. On one visit to the zoo, Margie counted 200 heads and 522 legs. How many of the animals that Margie counted were 2-legged birds? That's actually, I feel like that's actually pretty high for the number of animals or 2-legged birds in a zoo. I feel like from the time that I visit the Fort Worth Zoo, it probably wasn't that many, but it's okay. We'll cut MAA some slack. Now to do this problem, obviously it's a word problem, so we want to set up some system of equations to solve this. And the way we want to try to think about the systems of equations is, well, we know that, there's 2 really mystery variables here, the number of 2-legged birds and the number of 4-legged mammals. Well, so we can just say birds is going to be, B, and then mammals is going to be M. So our 2 variables are B and M. Now, the first thing we notice is that there's 200 heads. So obviously each bird has 1 head and each mammal also has 1 head. Unless there's some like mutant type of bird that I'm not aware of, we can safely assume that each of these has 1 head. So we can say that B plus M is 200. Now, we also see that there's 522 legs, so we know that each bird has 2 legs. and each mammal has 4 legs, and the total number of legs is going to be 522. So to solve this equation, what I'm going to do is I'm going to say that I'm going to multiply this first equation by 2. So after multiplying the first equation by 2, we know that 2b plus 2m equals 400. Now we can subtract these two equations and get that 2m equals 122, so m equals 61. Now we know that m equals 61, we can just go back and we can say, hey, well, m plus b is 200. We know that m is 61, so b is 200 minus 61, which is going to be 139 birds. So really interesting problem. And again, whenever you see these types of word problems, you just really want to set up a systems of equations and carefully manipulate until you get a final answer.
Yeah, awesome. Exactly as Kevin was saying. If anything, math problems are really good at giving you like suggestive activities to do when you're bored, because counting every single head and every single leg is crazy. Honestly, that is a lot of dedication to not lose track. Also, she could check her work just like we did to see if she gets a number that makes sense. But another way you could do this is pretty much the same thing, but writing these two equations, I used x as the number of birds and y as the number of mammals. I actually think using b and m is better because b also matches with birds and then m matches with mammals. But as long as you keep track of variables, it's fine. And then you can write this exact same two equations, except what I did with the x plus y is equal to 200 is I multiplied it by 4 because we want the number of two-legged birds. So we're looking for x. And so this multiplying it by 4, we also have this 4y in this equation, 4y in that equation. So we can cancel out the y's and it gives us x immediately. This is slightly faster. It might be, if you're like on a time crunch, then you might want to immediately just ignore y. But you could also solve for y and then plug it in to find x. I don't think it's that much slower. So, and perhaps maybe a second part of the problem immediately ask, what is the number of mammals? Although I've never seen a two-part question in AMC 8. But who knows, maybe they could do something different. Okay, so let's go to number 10. So, counting question. So how many 4-digit numbers greater than 1,000 are there that use the 4 digits of 2012? So what this is saying that we have a 4-digit number, 1, 2, 3, 4. It uses a 2, a 0, a 1, and a 2. So these are all individual digits. So immediately I'm seeing that 0 cannot go into the thousands place because first of all, that'll give us a 3-digit integer, which is not what we're looking for. And then it's also said that it's greater than 1,000. And so if we have a 0 in the thousandth digit, there's no way that we're going to satisfy that constraint. So we know 0 cannot be there. And then therefore, 0 is forced to be in one of these 3 slots. So we can just place that 0 first. So for the 0, we have 3 options because it can either be here, here, or here. So let's write down a 3. And then let's say, I don't know, 0 is here. Doesn't matter. It's just a placeholder. So now that we've taken care of 0, now we don't have to worry about it. So now we have this 2, this 1, and 2 in these 3 slots. So basically then we can say that pretend these 2's are different. So say this is 2 with a subscript 1. And then this is 2 with a subscript 2. And I'm realizing maybe this is bad notation because this kind of looks like I'm saying it's 2 base 1, 2 base 2. But this is just notation to say that these 2's are different. That's all. And then to arrange this 2 subscript 1, this 1, and this 2 subscript 2, well, then that's going to just be 3 factorial. Because in the thousands place, for example, we have 3 values that can go there. It can be any of these 3. And in the second blank slot, we've already used 1 of these 3 values. So there's going to be 2 ways. And then in the last slot, we're forced to place that remaining one. So 3 factorial. However, we have not taken into account that these 2's are actually the same. And in order to account for that, suppose I had, what's a random number? Like a 2, subscript 1, 2, subscript 2. And then, because right now we're counting this as the same as this, these 2 are the same, which is bad because these 2's are actually exactly the same. These 2 arrangements are supposed to be the same. So that's why we have to divide by 2 to account for this overcounting. Because for every case, there's actually 2 ways that we've said that we can arrange them when actually there's only 1, so we have to divide by 2. Okay, so now to actually grind out this calculation, this should be 3 times 6 at the top, which is 18 at the top, and then you divide by 2, which gives us 9, which should be answer choice D.
Oh, sorry, I was muted. Yeah, that's exactly right. And now we can move on to question number 11, I believe. And so question number 11 is kind of one of those generic mean, median, mode questions. And it just tells us that, the mean, median, and unique mode of 3, 4, 5, 6, 6, 7, and x are all equal. So what is the value of x? To this problem, I'm going to focus on the unique mode first, because I feel like this part is kind of the most interesting. Because essentially what this tells us is that all the numbers in 4, 5, 6, or 3, 4, 5, 6, and 7, every single number appears once except 6, because 6 appears twice. Now, so hypothetically, if x was equal to either, let's say, like 3, 4, 5, 6, or 7, so if x was anything that's like, or if x, I guess if x showed up as one of the other numbers in this list, that wouldn't work because then the mode wouldn't be unique, because let's say x was 3, right? We would have 2 3s and 2 6s, so there wouldn't be a unique mode. So the only way that x is a unique mode is if the only way there's a unique mode is if basically either x is something that's not at 3, 4, 5, 6, or 7. Let me use my stylus. 3, 4, 5, 6, or 7. So basically, either if x equals 6 or x does not equal 3, 4, 5, 6, or 7. So that's what the mode condition tells us. In addition, we know that the mean is going to be equal to this mysterious number. And by the way, we know that the mode being 6, or so, if either of these conditions happen, the mode equals 6, because 6 is the most common number. So we know that the mode equals 6, but we also know that the median and the mean also has to equal the mode, which is 6. So let's look at the mean first. So the mean tells us that 3 plus 4 plus 5 plus 6 plus 6 plus 7 plus x divided by the total number of positive integers there are equals 6, which is the mode. So what this tells us is that 3 plus 4 plus 5 plus 6 plus 6 plus 7, plus x, sorry, divided by 1, 2, 3, 4, 5, 6, 7, divided by 7 is going to equal 6, which is the mode. So this tells us 42 equals 3 plus 4 plus 5 plus 6 plus 6 plus 7 plus x. We can just add this together. So this is 7 plus 5 is 12 plus 12 is 24 plus 7 is 31 plus x. So we know that 31 plus x equals 42, so x equals 11, and that's our final answer.
Yep, that's exactly right. So the crucial step here is realizing that the mean, the median, and the mode have to equal 6, because we've used this unique mode condition, noticing that there's actually 2 6s when everything else, there's only one value. There's only 1 3, there's only 1 4, 1 5, and so on. And actually just from that information alone, we can rule out answer choices A and C, because we know it can't be 5 or 7, because otherwise this 6 is no longer going to be a unique mode, because suppose x is equal to 5. Now you have 2 5s and 2 6s. and there's not exactly a unique mode, so that's going to cause some problems. So if you get A or C, that's not good. The way Kevin approached it was perfect. He set up this equation here, which invokes this mean information. So adding up all the values, including x, and then dividing by 7, because that is the number of values we have, is equal to 6. And he found that x is equal to 11. We actually never use the information that the median also has to equal 6, but we can confirm just by writing the whole set. So we have 3, 4, 5, 6, 6, 7, and 11. Then if we actually find the median, then the median is also 6. So we are safe with our answer. So that's just some more reassurance that what we got was correct. All right, so that was a fun problem. Let's move on to number 12. Ooh, we're on double digits. I missed it when we got to double digits. Okay, so, ooh, it's only one sentence long. That could go bad. What is the units digit of 13 to the 2012 power? Okay, immediately when I see this, there's no way we're going to actually calculate that, because I don't think you don't get a calculator on this. And even if you had a calculator, this would be terribly painful. And certainly we're not doing this by hand. And I'm seeing, RC, you're saying that the units digit is going to cycle. Ooh, that's a good observation. So let's just write this as, we actually can ignore the tens digit, but let's just write the full thing. So 13 to the 2012th power. So actually we only need to be concerned with the ones digit, because the tens digit here isn't going to impact the ones digit. Because if I multiply something by 10, for example, well, we're just going to get a 0 at the end. That's not going to change the units digit. So we can actually just be concerned with 3 to the 2012th power. If we did this by hand, it's honestly not much better. So there must be a clever way. And RC mentioned how it's actually going to cycle. So what he means by that is, let's just say you have 3 to the first power, and we're only going to write down the units digit. Units digit. So 3 to the first has a units digit of 3. 3 to the second has a units digit of 9. And then 3 to the third, that's going to be 27. So the units digit of that is 7. And exactly as Grass said in chat, it's going to cycle 3971, 3971. And actually, let's write down 3 to the fourth as well. 3 to the fourth is 81, and that has a units digit of 1. And this is golden, because now if we multiply by another 3, we just go all the way back to where we started, because 3 to the fifth, this tells us that 3 to the fifth is also going to have a units digit of 3. So now we're back at where we started. Then we have 971, 3971, 3971, which is great because now we have a pattern. So now what we have to do is find where exactly is 3 to the 2012th on this scale. So let's see. So we can use mod in this problem. If you don't know what mod is, it's basically concerned with remainders. Like, for example, if I wrote 1 mod 4, then what this means is that this, whatever value, actually, let me write x is congruent to 1 mod 4. Don't worry if you've never seen this. What this is saying is x has a remainder of 1 when you divide it by 4. That's all this is saying. So for example, if x was equal to 1, that would work because 1, when you divide it by 4, has a remainder of 1. We love modular arithmetic. So 2012, well, on this scale, 2012 is divisible by 4, because for the divisibility rule of 4, we just look at the last 2 digits and see if that's divisible by 4. 12 is divisible by 4, so we know that 2012 is 0 mod 4. So I could write this as 2012 is congruent to 0 mod 4. Now, how is this supposed to help us from here to here? Seems like there's not really a correspondence. Well, actually, what this is saying here, well, if the exponent is 1 mod 4, because this cycles every 4, notice this. So this, if it's 1 as mod 4, the exponent, then it gives us a units digit of 3. You can see that here because 3 to the 5th is also giving us a remainder of 1 when you divide by 4, and that also has a units digit of 3. So actually what this corresponds to is now we look out of these 4, which of these exponents has a value of 0 when you divide by 4? Well, then it's going to be 3 to the 4, because 4 when you divide by 4 has a remainder of 0. So we know that this has to correspond. This 3 to the 2012 has to have a units digit of 1, which gives us our answer choice of A.
Yep, that's exactly right. And we can see here for this question just how important looking at so for whenever like you encounter these last digit problems, it's you can always like use I can't speak modular arithmetic to solve these types of questions, because modular arithmetic is so powerful because there's always going to be some sort of random pattern. Whenever you have these like crazy high exponents, you just want to look for a pattern and then look at, what happens at the very end after you divide everything out, basically. And so that was a really cool solution. Now we can move on to question number 13. So Jamar bought some pencils costing more than a penny each at the school bookstore and paid $1.43. Sharona bought some of the same pencils and paid $1.87. How many more pencils did Sharona buy than Jamar? Well, to solve this problem, we probably want to know, first of all, how much would each pencil cost, right? That's kind of like the main or the key point to this problem. Because if we don't know how much each pencil costs, then we couldn't really calculate how many more pencils Sharona bought than Jamar. So when I'm looking at this problem, I'm thinking about like prime factorization, right? Because we know that Jamar spent 143 cents on pencils. So and I think Sharona spent 187 cents on pencils. Now, if you've done like math competitions for a while, like I have, you can probably recognize immediately what these two like have in common, what factor these two have in common. But if you don't, let's do this step by step. So if we know that each, let's say that if each pencil costs C cents, then we know that C has to divide 143. And we also know that C has to divide 187 because obviously these people bought an integer amount of pencils. So which means that, if each pencil costs C cents, then obviously C has to divide both 143 and 187. So now let's try to prime factorize this. 143 factors into 11 times 13, and 187 factors into 11 times 17. And remember, C has to be greater than 1 cent because each pencil costs more than a penny each. So if each of these C's are more than 1, well, clearly the C has to be 11 because 11 is the only common prime factor. So now that we know that each pencil costs 11 cents, well, Sharona spent 187 minus 143, so she spent 44 cents more than Jamar. So since they spent 44 more cents, and each pencil costs 11 cents, well, clearly they bought 44 over 11, which is 4 more pencils, and that's how we solve this problem.
Yep, awesome. So yes, the key point is realizing that the pencils have to all cost equally. And so this might make us think of factors, because factors of these, if they're all the same, if you divide that by how much how much they paid by the number of pencils that they by how much the pencil cost, then we know how much that they actually bought. And another key point of this problem is that it said that, let's see, yeah, that these pencils cost more than a penny each. So we could have said that these pencils cost 1 penny, and that would have worked too. Those are ridiculously cheap pencils. And then say that Jamar bought 143 pencils, and then Sharona bought 187 pencils. That also would have worked. And that's why that singular phrase is there, that it has to be more than a penny. And that tells you that these pencils cannot be 1 cent. So that's why they have to be 11 cents. And yeah, someone said, I forgot who, but I thought this was funny, how you can't buy half a pencil. So you have to keep all of these values as integer values. So awesome, great observations. Let's go on to problem 14. Okay, so problem 14 says, in the Big N, a middle school football conference, each team plays every other team exactly once. And if a total of 21 conference games were played during the 2012 season, then how many teams were members of the Big N conference? Ooh, okay. This one seems scary, but we've got this. So the way I see this is like, suppose, like, let's just try smaller examples. So you can draw, yeah, exactly. So RC says you can draw something like a chart. So like, suppose we had 4 teams. Just pretend. That's not actually how many we have. And it's also not an answer choice. So we know team 1 over here plays against team 2, team 3, team 4. So that gives us 3 games. And then team 2 over here, well, we don't have to count that it plays with team 1 because that's already counted. So we only have to go this way to the right when counting. So team 2 plays games plays with teams 3 and team 4, so add 2 more games. And then team 3, we don't count this way because we've already included those games. So team 3 plays with team 4, and then that adds 1 more game. So we might see this pattern of a descending arithmetic sequence and how they differ by exactly 1, 3 plus 2 plus 1, which is pretty nice. So let's see if this pattern continues. Like, say we add 1 more team here. So now, pretending that this is team, let's actually move team number 1 from here to here. Team number 1 is here now. And this is team number 0, if that exists. So team number 0. Okay, well, this 3 plus 2 plus 1 already corresponds to the games that number 1 has played to the right. So all we have to do is add the number of games that team 0 plays just by joining in. We haven't counted those yet. So team 0 plays against 1, 2, 3, and 4, and we have not counted those, so we can add another 4 to this. And just by keeping track, 4 plus 3 plus 2 plus 1 is 10 conference games, so we're not quite done. So we have to add another team. Let's just see what happens. So team, oh, maybe I should have started with a higher number, because now I have to say team -1. But that's okay, we can pretend that exists. So now we've already counted these teams, so we just have to count the number of games that team -1 plays against these other teams just by joining in. Okay, well, team -1 plays against team 0, team 1, 2, 3, and 4. That sounds like 5 games, so we add another 5. And then 5 plus 4 plus 3 plus 2 plus 1 is going to be just 10, because we know 4 plus 3 plus 2 plus 1 is 10, plus another 5 is 15. So, oh goodness, we are still not done. So we have to add 1 more team. Okay. Yeah, I should have done different naming, because now we also have to do -2. Okay, team number -2. Okay, so we have this 5 plus 4 plus 3 plus 2 plus 1, which is this from this -1, so we don't have to count those. So with team -2, now we have to add the games that they've played. So they play against team -1, 0, 1, 2, 3, 4, which is 6 games. Yes, I'm regretting past decisions. And 6 plus 5 plus 4 plus 3 plus 2 plus 1, which is quite a mouthful, is equal to 21, which is exactly what we want because we know that a total of 21 conference games were played. Okay, awesome. Well, we're not quite done because the problem asks us how many teams were part of this conference. Well, that's just counting the number of dashes up here. So we have 1, 2, 3, 4, 5, 6, 7. which gives us 7 teams, and therefore matches up with answer choice B.
Yeah, that's exactly right, and that was also a great solution. Looking at looking at, I guess what types of teams play each other, and using that information to get the final answer. So that's really cool. Now we can move on to question number 15. So question number 15 says the smallest number greater than 2 that leaves a remainder of 2 when divided by 3, 4, 5, and 6 lies between which numbers? So to do this problem, again, we're going to have to use some modular arithmetic. If you guys know about modular arithmetic, basically the idea is that I'm going to write in terms of x is congruent to 2 mod 3, 2 mod 4, 2 mod 5, and 2 mod 6. And if you're not familiar with what that means, it basically just means that when you divide x, so when you divide x by 3, the remainder is 2. When you divide x by 4, the remainder is 2. So basically, x is congruent to 2 mod 3 means that x, when divided by 3, has a remainder of 2. Similarly for all three things. So that's basically what this notation means. So if we know that x is congruent to 2 mod 3, well, we can actually rewrite this as x minus 2 is going to be congruent to 0 mod 3. So this actually just tells us that 3 divides x minus 2. And now similarly, we know that 4 divides x minus 2, 5 divides x minus 2, and 6 divides x minus 2. So we know that, so let's write this: 3 divides x minus 2, 4 divides x minus 2, and so does 5, and so does 6. So if x minus 2 is divided by all these different factors, well, it has to be divided by the least common multiple of them. So it has to be divisible by the least common multiple of 3, 4, 5, and 6. And we just want to compute this, and so we know that that has to divide x minus 2. Now, how do we compute this? Well, we can see here that obviously we'll have to have a factor of 3 and a factor of 5. So we can start off by writing as 3 times 5. In addition, we obviously need 2 factors of 2 because we have a 4 here. And we have 1 factor of 2, but that doesn't matter. So we also need to multiply by 4. So the least common multiple is going to be 60. So 60 has to divide x minus 2. Now the least possible value of x that's not 2 obviously just has to be, equals, so it just has to be 62. Because, if x doesn't equal 2, well, the next possibility is that 60 equals x minus 2. So x equals 62. And that means x lies between 61 and 65, and so D is our final answer.
Yeah, awesome. I really liked in this problem how there's 2 ways that you can really think about this. The way Kevin did it, which is really awesome, is that knowing that 2 has to work, and then calculating the LCM of 3, 4, 5, and 6 to be 60, and then if you just add that to 2, well, you're going to get your answer. Or you could think of it in terms of modular arithmetic, writing this as that it has to be 2 mod and then something that relates with 3, 4, 5, and 6. And then also, well, separately, it has to be 2 mod 3, 2 mod 4, 2 mod 5, and 2 mod 6, which we can also write as 2 mod 60. This takes in this LCM idea as well, because notice how the 60 up here is the same as the one down here. So it says the smallest number greater than 2 that works. Well, we can't use 2 because that's not greater than 2. So we have to add another 60 to this to get a value that is also congruent to 2 mod 60, which is going to be 62, which gets us the same answer. And I think it's interesting how they had their answer choices not like specific values, and instead they had like these bounded values, like the 61 to 65. I'm not really sure as to why they did that, but I think that's pretty interesting. Maybe there's a quicker way of doing it or something. Okay. So for number 16, all right, we're getting into the harder questions now. So for number 16, it says each of the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 is used only once to make 2 5-digit numbers so that they have the largest possible sum. So which of the following could be one of the numbers? Ooh, okay, so this is kind of another counting question. Well, not exactly. Actually, this is number theory. Number theory is fun. So with this, well, intuitively, 9 has to be at the very left to make the largest possible sum. So what I mean by this is if you had these two 5-digit integers, this first one plus this second one, if you add them up, well, you're going to want to place 9 at the very left. Because if you place 9 here or something, well, you're going to waste this 9. The 9 is the biggest single-digit integer that you have. So you're going to want to place it here for sure. So 9 is going to go somewhere like here. And then again, intuitively, 0 is going to go all the way to the right. Because if, for example, you put a 0 here, that's a waste of a spot. Because let's say like it could have been an 8, for example. 8 is the next largest integer. If I had an 8 here, that would also help increase the sum. The reason why 8 isn't here is because then 8 is in the thousands place, but it could contribute in the 10,000s place, and this has a much larger impact. So just from our intuition, we know that 9 and 8 have to probably be on the leftmost. Oh, that is gone. Okay. 9 and 8 have to be on the leftmost. And then, yeah, so 1 also has to be at the rightmost too, because 1 is also not very helpful if it was all the way to the left over here. So we know 0 and 1 have to be somewhere at the very right. Actually, these could be switched and it would just be fine. There's no havoc that would be raised. So something that's interesting about these answer choices is, for example, like with answer choice E, like 0 is in this spot, in the tens place, but it's wasting that tens place because it could have been something larger, like say a 2, like a 2 could have been here, and it would have been way more helpful than a 0. So something like that tells us that option E cannot be correct. And then with A, with 7, 6, 5, 3, 1, well, that also can't be right because we know that these 10,000s places should probably be 9 and 8 to increase the sum as much as possible. We don't want it to be 7 when it could have been larger. So A probably can't be right. So if we do this more systematically, we can do this with the rest of the numbers. So we've already taken care of 9, 8, 0, and 1. So let's do the same thing with 2, 3, 4, 5, 6, and 7. So with 7, well, it's probably also going to be pretty left, because if it's somewhere to the right, then again, we're wasting not only the tens place, but we're also wasting a 7. We want the 7 to contribute a lot to this large sum. So 7 could be somewhere like here. It could be at the bottom, could be at the top, doesn't matter. Same thing with 6. 6 should also be pretty close to the left here, so we can just put 6 here. And then if we proceed with 5 and 4, again, those are the next largest numbers. So we probably want them to be pretty close to these 7s and 6s. So again, with the 5s and 4, let's say you have 5 up here, 4 down here. Again, we don't have to worry exactly where we place them. Like, for example, I could put 5 down here, 4 up here, and it would be exactly the same thing. We don't have to worry about that. So at the end, we can actually interchange any of these and then see if it matches up with the answer. Okay, yeah, you guys are saying to put 3 next. That's exactly right. So now we have 3 and 2, which the only places they can go is here. So pretty much done. So 3 and 2. All right, so, oh, okay, let's look at these answer choices. So we've already said how A and E cannot be correct because A has that issue of the 7 being too far to the left, and then E has that issue of 0 being also too far to the left. So we know A and E are not correct. So yeah, exactly as Grass said, just look at the answer choices. Has to start with 8 or a 9. The numbers go in decreasing order from left to right. Yes, exactly. Oh, I like how you said what you said about the decreasing order from left to right, because, like, for example, look at option D. D looks okay because 9 is all the way to the left and then 0 is all the way to the right, which seems to be fine. But then you look at the rest of the number closely. Look at this. So 9, 6, 2, 4, 0. Look at this 2 and 4. That's not good because this 2 seems to be really far to the left. Wouldn't it be better to write this as 9, 6, 4, 2, 0 if we swapped the 2 and the 4? Because we can immediately just take this number and find a better version of it. That sounds really mean. Oh gosh. Okay, don't cancel me for this. But 96420 is a better version of this because it maximizes the sum even more. So we know that D also can't be correct. So D, oh no, this is number shaming. This is not okay. Okay, we'll not say that again. Now we have to look at answer choice C and answer choice B. Oh, yeah, B also has this issue actually. So B, let's look at B. B says that it's going to be, one of them is going to be 8, 6, 7, 2, 4. Well, with B, there's actually two issues that are going on because we go from 6 and then up to 7 and then 2 up to 4. Well, I can just rewrite this as 8, 7, 6, 4, 2, which is going to contribute more to this sum than this would, because now we've moved 7 more towards the left, which means left is this way, left. So it'll contribute more to the larger sum. And same thing with this 4 and 2. If we move the 4 more to the left, then it's going to help more. So we know that B also can't be correct. So therefore, our answer has to be C, which we know works because it's 87431. So we can actually just do this. Like we have this 8 over here, this 7 up here. We can just switch the 7 and 6s and that would be fine. Then it has a 4. We can again switch the 4 and, oh, it's already there. The 4 is fine. And then the 3, we can switch the 3 from up here to down here, and then we get the same thing. So it seems like answer choice C will optimize our sum.
Yeah, exactly. And that was actually a really smart idea. Examining the answer choices and like making sure that, checking if each one works or not to get the final answer. That was a really nice way to do the problem. Moving on to question number 17, we see that a square with integer side length is kind to 10 squares, all of which have an integer side length and at least 8 of which have area 1. So what is the smallest possible value of the side length or the length of the side of the original square? So this problem is kind of like weird because there's not like really any obvious way to do this. So I guess if we just start by looking at this problem, right? So we have a square which is kind of 10 squares, and all of them have integer side length and at least 8 of which have area 1. So you want to figure out the smallest possible value of the side of the original square. Okay, so I'm going to do like something a bit tricky here, which is that instead of looking at the side length of the square, I'm going to look at area. And that's, so if we look at the area, right? So let's say the area of the larger square. So let's say x is the side length of a larger square, right? So the larger square side length is going to be x, and we're kind of partitioning this into 10 squares. And we know that at least 8 of them has area 1. So this tells us that x squared is going to equal 8 squared, or sorry, not 8 squared, equals 8 times 1 plus area of the two other mystery squares. But we also know that, obviously each of these squares has area at least 1, right? Each of these squares has area at least 1 because the side length is a positive integer, so the area of each of the smaller squares is at least 1. This means that the total area is going to be at least 10. So x squared is going to be at least 10. So x has to be greater than or equal to 4 just by looking at this. Because if it was 3 or less, then the total area of the 10 squares would be 9, which is obviously impossible. So now that we know that the area of the larger square is at least 4, let's try to see if we can get 4 to work. So let's try to see if we could make 4 work, because if 4 works, then obviously it has to be the smallest possible value. So to get 4 to work, let's just draw this little square here. Basically, you know, we know that the total squares area is 16. We have eight smaller squares, each with area 1, and we have 2 squares of mystery side length. Let's just say it's A and B. And we know that A8 equals A squared plus B squared. And A and B are the mystery side lengths of the remaining 2 squares. Obviously, A and B have to be at most 2 because otherwise, if it was more than 3 or greater, then the right-hand side be at least 9, which is a contradiction. And, you know, just examining this tells us that A and B both have to be 2. So we have 2 2x2s and 8 1x1s. And so with that in mind, it's pretty easy to just construct this diagram. Basically, we just know that we have 8 2x2, or we have 2 2x2s, so each of these are going to be 2x2s, and we have 8 1x1s. And we can pretty easily check that, you know, this actually works for the 4x4 square. So we showed that 4 works, so 4 is going to be our final answer because it is as small as possible.
Yeah, perfect. So the way that Kevin did it is absolutely right. So realizing that 3 cannot possibly work because if it's 3 by 3, even making all of them 1 by 1 squares isn't going to give us 10 squares. So we look to the next largest case, which is 4, and we can construct this box over here, which works perfectly. So yeah, awesome. All right, so let's move on to problem number 18. So 18 asks, what is the smallest positive integer that is neither prime nor square and has no prime factor less than 50? Ooh, okay, this one's fun. More number theory. Okay, so immediately we can think of what factors would go into the smallest positive integer. Like for example, this integer isn't going to have factors of 2, 3, 5, and literally anything less than 50 isn't going to work. Like, can 51 work? Well, no, because 51 is divisible by 3, divisible by 17. And so those are less than 50. So even though 51 is more than 50, it has factors that are less than 50, which inherently makes it so that 51 doesn't work. And I saw that, Monkey, you said that you can find something like 53 times 59, which is absolutely right. So the reason why it has to be, we have to involve 53, 59 specifically, is because say, if has a factor of 53, 53 is fine because it's prime, and so it won't have any factors less than 50. And then we have to actually multiply it by something else because it tells us that this integer is not prime. So we have to find something else. So 53 we know works. So then we find the next prime integer. So we can kind of just count up from there. So 54 can't work because it has a 2. 55 can't work because it has a 5. And then 56 can't work because it has a 2. 57 has a 3. 58 has a 2. And then we finally approach 59, which is also prime. And that's the jackpot because 59, well, not only is it greater than 50, it's also prime. So that means it can work in this factor. So all we have to do is to actually just calculate 53 times 59. So let's not make any sillies because we're in the final stretch. So we just multiply this out. We get 5 here, carry the 4 to get 2950. Then you multiply the 3 with the 9, 27. Carry the 2, then you get 177. Then you just add those together, get 1, carry the 1 here. Then you get this, carry another 1, and this gives you 3,127, which matches up with answer choice A. And it's pretty comforting that it's also the smallest value out of the answer choices.
Yep, that's exactly right. And now I think we're almost getting to the final 5. A few more problems to go. So in a jar of red, green, and blue beans, all but 6 are red, all but 8 are green, and all but 4 are blue. So how many marbles are in the jar? So to do this problem, again, we want to probably set up a system of equations. And to do that, let's just say red, so let's say red equals R, green equals G, and then blue equals B. And so that's going to be our systems of equations. Well, now we know that, and we're going to say that S is going to be R plus G plus B. So we know that S equals R minus 6, oh sorry, X equals, so S minus R equals 6. S minus G equals 8. And S minus B equals 4. And just to explain how we got these equations, right? So in a jar of red, green, and blue marbles, essentially we know that all but 6 are going to be red, all but 8 are going to be green, and all but 4 are going to be blue. So all of the marbles except 6 are going to be red. So what this tells us that since S is the total number of marbles, minus 6, so minus R of them, it's going to be like everything else, basically, if that makes any sense. So that's how we get S minus R equals 6, S minus G equals 8, and S minus B equals 4. So if we add all these equations together, we get 3S minus R plus G plus B, which remember is equal to S, equals 6 plus 8 plus 4, which equals 18. So 2S equals 18, so S equals 9. And that's how we figure out this problem. And the main idea here is after you just set up a system of equations, you just want to manipulate, such as adding all of them to get a final answer.
That's exactly right. So I really like what Kevin did with just immediately converting all the word soup into some equations over here. So here just trying to represent everything with different colors. The main realization is that G plus B has to equal 6 because it says all but 6 are red marbles. So this is telling you that the green ones plus the blue ones have to be 6 because those are not the red marbles. Then you write the other corresponding equations, then you add them all up because we want R plus G plus B ultimately. R is the number of red marbles, G is the number of green marbles, and B is the number of blue marbles. So if we add all of them together, it gives us this nice line over here of 2R plus 2G plus 2B. And this is just twice the number of what we need because we're just looking for how many, not twice the number of total marbles. So yeah, this is a pretty sleek problem. I really like this one. All right, so now we're getting into the 20s. Scary. All right, so number 20. Not quite the final 5, but we're almost there. So number 20 asks, what is the correct ordering of the 3 numbers 5 over 19, 7 over 21, and 9 over 23? Ooh, okay. So none of these have a common denominator, which could be bad, but we've got this. So let's just write them all out. So we've got 5 over 19, 7 over 21, then 9 over 23. So immediately what I'm seeing with this one is how the denominator is increasing by 2. So notice from when we get to 19 to 21, you add 2. From 21 to 23, you add another 2. And then at the top, it's the same thing. At the top, you have 5 to 7, you add 2. And then 7 to 9, you add another 2, which is a pretty interesting coincidence. Probably isn't a coincidence that both of these, you just to get from one fraction to another, you just add to both the numerator and denominator by 2. Now, I like what some of you are saying here about how we can just compare 2 fractions and then take the bigger one and then compare it to the other one. That's a really good way of doing it because comparing all 3 of them at the same time, like you have to find a greatest common denominator of 19 times 21 times 23, which honestly, oh goodness, that is disgusting. I do not want to multiply all those 3 numbers. That's terrifying. So there's probably a sleeker way of doing this. So noticing this pattern of adding 2 to the top and the bottom, we could just take advantage of this pattern. What if I rewrote this as 5 over 19? What if I rewrote that as 19 minus 14 over 19? And then I rewrote this one, 7 over 21, as 21 minus 14 over 21. And then I rewrote 9 over 23 as 23 minus 14 over 23. Well, you might be asking, why did you do this? Like this seems to go backwards because now we have two values in the numerator, which seems to be worse than what we had before. Okay, well, calm down, it's okay. First thing we can do is just to confirm that this line is the same thing as this one. So 19 minus 14 is 5, 21 minus 14 is 7, 23 minus 14 is 9. So we haven't broken any laws here. It's completely fine. Yeah, we don't have to raise the panic alarm or anything. We're completely fine. So then I might notice that this 19 over 19 is equal to 1. So I can rewrite this as 1 minus 14 over 19. Well, you might be asking, why is this helpful? Well, let's look at the next one. We have 21 over 21 over here, and then a minus 14 next. So again, we can write this as 1 minus 14 over 21. Now you might notice something, because in both of these, we have a 1 minus a fraction. And in both of these fractions, we had a 14 at the top. So maybe we get something similar in the last fraction. Let's just see. So same thing, 23 over 23 is another 1. So you have a 1 down here, minus 14 over 23. Interesting, because we have a 14 over something subtracted from a 1 in all three of these. There's no way this is a coincidence. So let's just look closer at each of these. So all of these have a fraction minus a 1. So this second fraction, like for example, let's compare 14 over 19 versus 14 over 21. So 14 over 19, is that greater or less than 14 over 21? Well, we can just compare, like say 1 over 19 and 1 over 21, dividing both sides by 14. And we know that 1 over 19 has to be larger than 1 over 21. Like think of a pizza. You'd much rather get 1/19 of a pizza than 1/21 of a pizza, right? Even though 21 is larger than 19, well, when we put that in the denominator, well, 1 over 19 is going to be greater than 1 over 21. So we know that 14 over 19 has to be greater than 14 over 21. Okay, well, now that we know this, what does this tell us about 1 minus 14 over 19 versus 1 minus 14 over 21? Well, actually, we can just rewrite this whole inequality that we got at the bottom. So let's move down a little bit. So don't worry, the stuff at the top is still there, so we can refer to it. So with this, what if I added 1 to both sides? That's not illegal because 1 plus this is still going to be greater than 1 plus 14 over 21. So that's not illegal. Let's just add 1 to both sides. So if we do that, okay, well, this is really, really close to what we want. We're looking to compare 1 minus 14 over 19, 1 minus 14 over 21. But right now we have 1 plus 14 over 19, and then 1 plus 14 over 21. We're really close. So we can move this to the other side. Move the 14 over 19, subtract it from both sides. What does this do? So let's rewrite this. So now we have 1 is greater than 14 over 21 plus 1 minus 14 over 19. Okay, awesome. This at the right side looks like what we want because this 1 minus 14 over 19, that's exactly what's up here. So let's do the same thing to the 14 over 21. Subtract that from both sides. Okay, so then we have 1 minus 14 over 21 is greater than. Now note that we haven't changed this greater sign at all. So this whole thing is always true. And then this is greater than 1 minus 14 over 19. Well, we've just discovered something. We are just told from this equation that 1 minus 14 over 21 is greater than 1 minus 14 over 19. So now we can go back up here and erase this comma and put this sign over here. So we know the 1 minus 14 over 21 is on the greater side. So we want this to face that way. So now just have to compare that to this over here. Now you can think about this in another way, which smooth this down. Let's compare 1 minus 14 over 21 versus 1 minus 14 over 23. If 1 minus 14 over 23 is greater than this, now we know that is also greater than this. We have a chain of inequalities. So just comparing these two, well, we have a 1 minus a 14 over something. Well, we can think about it this way. Again, 14 over 21, we know that's going to be greater than 14 minus 23, because same idea with the pizza. If you had 1/21st of a pizza, that's better, or assuming that you like pizza a lot and you're not lactose intolerant, then that is better than a 23rd of a pizza. So that means 14 over 21 is greater. Okay, well, in this case, you're subtracting it from 1. So the more you subtract, the less that is going to be. So therefore, because in this one, the 1 minus 14 over 23, we're subtracting less overall versus subtracting 14 over 21. And we're always subtracting from the same thing, from this 1. So that means that 1 minus 14 over 23 has to be greater than 1 minus 14 over 21. So that means that we can safely say that the inequality sign faces this way. Okay, let's move back all the way up here from where we started. So moving back up, we know that these are all in the same order. So we can write this inequality chain in the same order as well. So we can say that it's going to be like this up here. Notice how this 9 over 23 is greater than 7 over 21, is greater than 5 over 19, just like what we said down here, because these two are equal. 1 minus 14 over 23 is equal to 9 over 23, because when we went down this way, we didn't do anything illegal or anything, so we can go back up just the same. So this tells us that we have this chain of inequalities, which tells us that our answer is going to be B. Oh, Kevin, I think you're muted.
Oh shoot, yeah, sorry, my bad. So yeah, thank you. And I know that that was kind of a lot, but I guess the main idea is just that you want to try to compare each of these three, or you just want to compare each of these three fractions and be careful to not make any silly arithmetic mistakes, and then finally you can get an answer. And I know it's kind of a lot, but sometimes that's how the AMC is. Unlucky, I guess. So now we can move on to question number 21, which says that Marla has a large white cube of edge 10 feet, so she also has enough paint to cover 300 square feet. And she uses all the paint to create a white square centered on each face, surrounded by a green border. And want to know what the area of each of these white squares is in square feet. Well, so, first of all, we know that the total surface area of the cube is going to be 6s squared, right? Where s is the side length, because there are 6 faces, and each of the faces is just a square with side length, or with area, 10 squared, because the edge, or the side length is 10 feet. So the total surface area is going to be 600 square feet. And she has enough paint to cover 300 square feet. And she uses all the paint to make a white square centered on each face, surrounded by a green border. So, since there are six faces, since there are 6 faces on the cube, well, then each face is just simply 300. Sorry. So each face is just going to have 300 divided by 6, which equals 50 square feet of green paint on it. And remember that sorry, I should probably recap. So basically, there are 600 total square feet, right, of the cube, and each face actually has 100 square feet of total area. And so, we've already painted 50, and we have enough paint to paint, exactly 300 square feet. And so she uses all the And so she uses all the paint to create a white squared center on each face. So essentially, we're using, since there are, 6 different faces, and obviously she divides it equally. Well, she applies 300, or not 300, 300 divided by 6, which equals 50 square feet of green paint per face. So the total area of each face is 100, and she uses 50 to paint, something green, paint the border green. So the area of the white square that's left is just going to be 100 minus 50, which is 50. And that's how we solve this problem. And notice that this was like quite a bit easier than some of these other problems. And so this kind of shows you that like on the actual AMC 8, you want to try to, I guess, like don't be scared that's number 21 and it's like really far back and like it's supposed to be really scary, because sometimes these like later problems are actually like pretty easy, and sometimes the earlier problems are actually like kind of hard. So just be aware of that, and like don't feel like, if you can't solve number 13, like like you just like, don't get like stuck in an infinite loop of solving a problem that's, really hard for its position. And also, I guess on the converse of that, try to solve some problems that are later on, at least take a look at them and see if they're easier or not.
Yeah, exactly as Kevin was saying. So this problem here highlights the importance of looking at the later problem, because look at number 20, for example, with all of like the work that was all over the screen. Like I had to move things down, move things up. And this one, I just used this much space. And that doesn't necessarily mean it's easier, but it certainly took a lot less time to do this one. So that doesn't necessarily mean like the harder problem or the later problems are harder. Usually it's pretty like usually it progresses that way, but sometimes like there's kind of like weird spikes. Like for example, in this case, 21 seemed easier than 20. I mean, if you thought 21 was harder than 20, that's also fine, because I know geometry and algebra, each person has their different preferences, different strengths. So maybe this one was harder for you. So it's important to look at all of the problems and to recognize your strengths. Like if you're good at algebra, you know that, then you're going to go into the test and you're going to want to find algebra problems, but you don't know which ones are algebra problems. Like it could be like number 1 is an algebra problem, and then all the way down, number 21 is also an algebra problem, but you don't know that going in. So you need to look at all of the problems to see which ones are going to play to your strength. So just a test taking tip. And I'm not sure when the AMC 8 is, but it's coming up pretty soon. So yeah, that's a good tip to just keep in mind. Okay, let's look at number 22, which is pretty far into the test, but we've got this. So let R be a set of 9 distinct integers. 6 of the elements are 2, 3, 4, 6, 9, and 14. So what is the number of possible values of the median of R? Okay, just by looking at this, we want to make these sentences words into math. So R is a set of 9 distinct integers, and we know 6 of them. So in R, we know that, and this funky notation, I believe just means that R is that set or something like that. Or I'm not sure. Let's be safe and use something else. Equals. Okay, so we know 6 of them are 2, 3, 4, 6, 9, and 14. And there's 3 other ones that we don't quite know yet. So question mark, question mark, question mark. We don't know where they are relative to it. We pretty much know nothing about it, except that it's not any of these values, because we're given that they're distinct integers, all 9 of them. Okay, so it asks for the possible values of the median. Okay, well, if I have 9 integers, let's just write 9 slots to represent them. They could be anything. 3, 4, 5, 6, 7, 8, 9. Okay, well, the median of the 9 integers is going to be right in the middle, right here. So this, whatever is in that spot, right here, is going to be the median. So we know that in the median, there's going to be 4 values that are less than it, 4 values that are greater than it. So in this case, in R, we want to find the values that are possible to be sandwiched in the middle right here. So let's just look at that. So suppose all of these 3 integers are all greater than 14. let's say they're 15, 16, 17, just to make things easier. So if we have that, and it's nice that they put them in order of increasing, in increasing order. So we have 2, 3, 4, 6, 9, 14, and just pretend it's 15, 16, 17. Okay, well, we know 9 is possible now because 9 is sandwiched in the middle. So we know also what we know from this is no matter what these green ones are, we will never be able to achieve a median that's greater than 9. Because even if you increase these values, they're still going to be on the right of this 9. I can make them like 50 gazillion and other ridiculous values, and this 9 is still going to be the median. It does not matter. Like I can even make them like 10, 11, 12, and they'll be here. They're still going to be at the right of this 9. So no matter what, we know 9 is the largest possible median. So 9 is the largest possible median. We'll just note that up there. Okay, well, this leads me to think, what is the smallest possible median? Because if we just use this strategy, maybe we can bound the possible values of medians. So let's erase everything. Let's see. So what if all these green values, what if they're all less than 2? Say like -1, 0, 1. So let's just write those down. So suppose they're -1, 0, 1. Well, what is the median now? So we write the rest, 2, 3, 4, 6, 9, 14. Okay, well, we look at the middle and we have a 3. So a 3 is going to be a median here. So 3, using the same logic as earlier, 3 is going to be the smallest median that we can achieve, because no matter what these question marks are, remember these, the -1, 0, 1, they could be anything. They could be -2, they could be -50 billion. Who knows? It doesn't tell you. But no matter what they are, as long as they're less than 2, well, this tells you that 3 is still going to be the median. It does not matter what these are down here. So that means the smallest median is going to be 3. If we use this reasoning, well, we might guess that it's just going to be everything from 3 to 9. And we can prove that, like, for example, like 4 can be the median. We can make any of these values medians from 3 to 9. So for example, if you aren't convinced, we can make 4 a median. So let's just erase all that. Oh, maybe I shouldn't have erased the dashes. Okay, so I erase all of this. Okay, well, if we want to prove that 4 is a possible median, let's make it a possible median. Let's put it all the way in the middle, put it here. So we've already got 4 down here. So what makes it possible that 4 is the median? Well, we can write down the other numbers. So we know 2, 3, 6, 9, 14. We can shift these around if we want. Like we can put 2 here, for example. We can put whatever. It's fine, as long as we have these blank spaces. Okay, well, these blank spaces can be whatever we want, right? Because we can have this blank space be 0, -1, 15. Boom, we've created a set R that 4 is the median. Okay, well, if you still aren't convinced, let's go to 5. Why is 5 possible? Okay, if 5 was the median, then we've used up one of these integers that we don't know. So we only have 2 slots left. So we can write 2, 3, 4, which we know are already in the set. So then with 5 in the middle, we have a blank one here and a blank one over here. That means that 5 is a possible median because we can make these whatever we want and we'll be fine. So 5 is possible. And if you still aren't convinced, which is fine, it's perfectly good to be a skeptic because maybe there's something from 3 to 9 that doesn't work. And then you'll be stumped and then you put in a wrong answer and then later that will be terrible. But so that's why it's good to also question these. But I can say that everything from 3 to 9 is possible. If you want, you can also just prove and make sure that you can create a set R such that those medians are possible. But enough of that. So we know that the medians are going to be every value from 3 to 9. That means the median can be 3, 4, 5, 6, 7, 8, and 9. And this looks like that's 7 possible values, which is going to correspond with answer choice D. Oh, Kevin, I think you're muted.
Oh, I'm so sorry. I keep forgetting.
It's okay.
Yeah, thank you. And now I think we're going to be on to our final three. So an equilateral triangle and a regular hexagon have equal perimeters. If the triangle's area is 4, what is the area of the hexagon? So this is a really interesting question. So let's look at this, right? So if I have a hexagon, let's say I have a hexagon here. I know, marvelous drawing. And if I know the triangle's area is going to be 4, I want to know what the hexagon's area is if they have equal perimeters. Well, if they have equal perimeters, then remember, a hexagon has 6 side lengths, right? So if each of these is like, let's say S, right? That means that 6S is going to equal 3 of the triangle side length, which let's just say is like, I don't know, N, right? So essentially what this tells us is that the triangle side lengths are twice as big as the hexagon. So basically the triangle side length, the triangle side length is going to be twice as big as the hexagons, right? And this means that, if we have a triangle, let's say with 2S, 2S, and 2S, well, that's the triangle that they're talking about. And the equilateral triangle's area is going to be 4. And if we shrink this triangle by a factor of 1/2, well, if we shrink it by like 1/2, so it's just S, S, and then S, this area is just going to be 1, right? We can see this because we know that this area is going to be 4. Again, remembering that the triangle side lengths are twice as large as the hexagons. But now if we divide our regular hexagon into 6 shapes like this, like we're cutting a pizza, well, we actually have 6 equilateral triangles. And each of these equilateral triangles have side length S. So each of these equilateral triangles have area 1. So we have 6 triangles, each with area 1. So the total area of the entire hexagon is just 6 times 1, which is 6, which is our final answer.
Yeah, perfect. So I really like this geometry question because it really tests your knowledge of proportions and how area is related to length. So you might think that length is proportional to area, which isn't quite true because think of a square. If you increase a square's length, all of the sides, by 2, by a factor of 2, for example, you had a square of length 1. Now you have a 2 by 2 square. Well, the area of that is actually going to be 2 squared because notice how like the 1 by 1 had an area of 1. The area of the square that was 2 by 2 is an area of 4. So you have to make sure that you realize that area is actually proportional to the length square. And I really like how Kevin transformed from this larger triangle, which is supposed to be a length of 2S. This is not to scale. But this, if you convert it to the smaller triangle within the hexagon that has half the side length, then the area has to be 1/4 of the way it was before. And then, of course, there's 6 of them. Okay, so let's go on to 24, which is yet another geometry question. So number 24, it does love hard geometry questions. So 24 says that a circle of radius 2 is cut into 4 congruent arcs. These 4 congruent arcs are joined to form the star shape shown. What is the ratio of the area of the star figure to the area of the original circle? Okay, well, in this diagram, it doesn't tell us anything. So let's use the information we're given and just label things. So we're told that this circle has a radius of 2. So that means this right here, this length, let's say that this is the center, this dot. So this from the center all the way up to there is going to be equal to 2. So that's some good information. Actually, just from this, we can immediately say that the area of this circle is 4 pi. Why? Because the area of a circle is pi r squared, and we know that the radius is 2. So we know that this is 4 pi. So yay, we solved half the problem. Now we have to look at the scarier shape, which is this weird star-looking thing. Okay, so, well, what if I connected this point, like drew this point straight down, and then this point straight left? let's just see what happens. Because when you have weird shapes, sometimes you want to be drawing lines that could be helpful. And it seems like if we just connected those, like it might make some sort of rectangle. So let's just draw that. So I'm seeing that some of you are saying that this is going to give us a square, which is pretty helpful. Okay. And we're told that these actually look like perfect quarter circles. Pretend these lines are straight. And we are given that, again, the circles of radius too. And all they did to make this star figure was they took a quarter circle, for example, this part over here. If I connected these over here, shade those in, they just turn this arc in. So essentially this quarter circle is equal to this quarter circle here, because they're the same thing. So let's see exactly what that tells us. So now we know this length from here to here is going to be equal to 2. So 2 right here. All right, well, what this tells us is that the length of this entire side here is going to be 2 plus 2, because we have 2 of these quarter circles. So therefore, that entire length is 4. And we can say the same thing about this length too. That is also going to be 4, because we know this is 2, that is 2, adds up to 4. So the area of this entire square is going to be 16. Okay, now that we have 16, we want the area of this star shape. And it seems like we've included a lot of parts that we don't want, these 4 quarter circles, which the area we just found earlier, we found that the area of this circle is 4 pi. Well, these 4 quarter circles, if you add them all up, they're going to be equal to this entire circle. So all we need to do is subtract the quote-unquote bad area, which are these quarter circles, and then we get the area of the star. So all we need to do is 16 subtract 4 pi from that. And then because we're looking for the ratio of the area of the star figure to the area of the original circle, then we just put 16 minus 4 pi, put that over 4 pi. And then we notice that the factor of 4 could cancel. So we get 4. Actually, just write this as 4 times 4 minus pi over 4 pi. The 4's cancel, which is nice. And then this gives us 4 minus pi over pi, which corresponds with answer choice A. All right. I think, yeah, that's all for this one. Okay, Kevin might be frozen. I'm not really sure what's happening.
Oh,
Oh,
sorry.
he's back.
I was trying to unmute. It's a struggle. Yeah, that's a great solution. And I guess like that was I guess it's kind of similar to the number 23, right? Where we just like want to like manipulate the areas and try to like make sense of like some weird complex shapes. And so that's kind of similar. But now we're on to the final boss. It's question number 25. And this question, so for this question, we have a square with area 4 inscribed in a square, or inscribed in a square with area 5. And oh my, this is a mouthful. Which each vertex of the smaller square on a vertex of the larger square. A vertex of the smaller square divides the side of the larger square into 2 segments, one of length A and one of length B. What is the value of AB? Okay. So this problem is, so like when I'm looking at this problem, right? Here's the thing, right? It tells us a lot about areas. So it tells us, so I guess, okay, let's take a step back, right? So first of all, we know that the larger square has area 5, so the side length is root 5. We know that the smaller square has area 4, so the side length is going to be 2. Now, one way you could solve this problem is you could like set up equations. So let's say a plus b is equal to root 5, and then we know that a squared plus or a squared plus b squared equals 2, or sorry, not equals 2 squared, which is 4, and we could solve the system's equations that way. And let's just do that. So we know that a squared plus b squared equals 2 squared because of Pythagorean theorem on this triangle. So a squared plus b squared equals 4, and then a plus b equals square root of 5 because it's just the side length of the larger square. So now we can see that squaring both terms here, a plus b squared equals 5. So a squared plus 2ab plus b squared equals 5. We know that this is going to be equal to 4. So we just get that 2ab equals 5 minus 4, which is equals 1. So ab equals 1/2. So that's the first way you could solve this problem. But I'm just going to go over one other way that you could do this problem. So the other way you could look at this problem, and it's like more geometry based, is that we know that the larger square has area 5 and the smaller square has area 4. And this means that like these 4 small triangles, this total area is going to be 1. So each of these small triangles, like this triangle right here, its area is going to be 1. So AB over 2, or sorry, not 1, 1/4. So AB over 2 equals 1/4, so then we could solve it that way and get AB equals 1/2. But either way, we could do it algebraically or geometry, or we could use geometry, but the final solution is going to be 1/2 to solve the problem.
It's awesome. And even though this is number 25 from seeing some of your say, it's not actually that bad. And I like seeing that because honestly, like when I first saw this question, I was like, how are you supposed to get an AB here? Because this seems to do a lot with areas and not much of like actually multiplying this A and B together. So I really like what Kevin did of mentioning the first method, which you can take the area of this whole thing, this whole square, and then subtracting the inside square and then getting the area of the small triangles. So like what he said is a plus b, since that's the length of the entire side length squared to find the area of that. That's equal to 5. That's what we're given. So then we can find the area of the inner square, which we are also told has an area of 4. And the side length of this square, we know is going to be square root of a squared plus b squared, because Pythagorean theorem on right triangles. And if we square that, then that gives us the area of this square. So yeah, exactly as Kevin said, a squared plus b squared is equal to 4. And then in here, if you expand the a plus b squared, then you get a squared plus 2ab plus b squared. And then you can cancel out with this. And then you get that ab is equal to 1/2. And then the other way, which Kevin also mentioned, was realizing that a times b is just the almost area of this triangle. The area of this triangle is actually just a times b over 2, but what we're interested in is the AB. And then we can just put this in terms of area, and then we get the same thing, which AB is equal to 1/2. So it's nice that using these two different methods, we get the same answer, because while maybe we made the same silly mistake in both, that's honestly pretty improbable. So the fact that we got the same answer, we can be pretty confident that our answer's right. So yay, we did the entire AMC 8. I don't know how long we took on it, but hopefully everything made sense here. If not, you can ask a couple of questions, but that is all for today. So yeah, thank you all for coming, and good luck on the AMC 8. I don't know when that is, but I heard it's pretty soon. So best of luck.
Good luck, everyone, and have a great rest of your week. Bye. Bye, everyone.
Bye. Thanks for coming. Right, I have to hop off, but it was really great working with you today. Thanks so
Yeah,
much.
yeah, thank you. Have a great week.
Bye, you too.
Bye.